All right, so the lab assignment today, I think it should only take 20 to 25 minutes, but it took all the students here in Dr. Harbor's section pretty much the full time, and it took the last group that I had around 40 minutes to complete. So we're gonna try to get to that as quick as possible. That being said, does anybody have any questions regarding today's in-class assignment or any homework problem or anything like that? Of which assignment, please, sir? All right. Let's see. Wait, problem 3 from homework 2. Sorry, I got it backwards there. All righty, let's see if there's anybody on Zoom to even bother sharing. Oh, yes, there is. All right, so let me share the screen. This one. And let me mark Mr. Bustamante here, since he's on Zoom. All right, let's get back to that. All right, so we were asked to find the power absorbed by each of the 5 elements. So this is an example of a single loop circuit, right? Because all of the elements are connected in series. So what circuit analysis technique should you probably apply here? Because it's a single loop circuit. KVL, right? So let me pop over to this guy. And copy down the circuit real quick. B1 8010. And B1 for me is 6 volts. All right, I think that's all of the information. Yeah. So let me share the correct screen with Mr. Bustamante. All right, so we need to assign a direction for our current because we weren't given one. So what direction would you care to use, clockwise or counterclockwise around this oddly shaped loop? Counterclockwise, all righty. So that means that we're going to go around this way, and let's just call this current, for the sake of argument, IY. So it's got a different name than the IX. So we're following it around this path. So all of these currents that I've drawn represent the exact same current IY because it's a single loop circuit. So where do you want to start writing our KVL equation? All right, so let's start here, and we're going to follow it counterclockwise. So we have negative 3Vx plus positive Vx, and now we need to have a voltage drop over our 10 ohm resistor, and we're also going to have to assign one over our 80 ohm resistor and our 70 ohm resistor. So what I'm going to do is I'm going to assume that the positive polarity terminal is here, negative here, positive here, negative here, positive here, negative here for each of these guys, so that the current is flowing into the positive polarity terminal, because that allows me to say, if the current's flowing into the positive polarity terminal, then my expression for those voltages I won't have to add an extra negative sign in like we discussed in the last class. Now, because for the sake of time, we know using Ohm's law that the voltage drop over the 10 ohm resistor is just going to be the 10 ohm resistor times the current flowing through it, right? So instead of bothering to assign it, say V10, et cetera, I'm just going to call that plus 10 ohms times IY. And then I see minus 6 volts. Then I'm going to see plus 80 ohms times IY. And finally, plus 70 ohms times IY is equal to 0. So I now have one equation with two unknowns. So how am I going to relate the quantity Vx to the current IY? Well, let's just use Ohm's law, right? Vx, by definition, is the voltage drop over the 40 ohm resistor. Positive polarity on the right, negative polarity on the left. So how can I write an Ohm's law equation to put Vx in terms of IY? Yeah. And so now we have enough information. We can substitute in this 40 IY into Vx, and we can solve for that current IY that's flowing around everything. And that will allow us to calculate all of the powers, because IY squared times any of these resistors gives us the power absorbed by the resistor, and IY multiplied by the voltages gives us the power absorbed or supplied by each of our sources. So once we know IY, finding literally everything else about the circuit is trivial. So are we good? All right.